guys, so this one is about getting shear force and bending moment and axial load if that exists, okay, located in one particular point, and in this particular point B, okay? So we have our beam, okay? We will assume that it's, attached to the wall here at A, and it has this length of 15 feet, okay? And it's subject to this distributed load that it's being applied above it, okay? So here we have the maximum here, and we have this triangular distribution. Okay, so this one, it's a typical problem in statics, that in order to know certain things, and in this case we want to know something happening there. So what I'm going to do here, the typical way to put it is a distribution, and a distribution is, let's see how the variable, in this case shear force, will look along the length. So in this case, this is the length, and I also going to put this one, so for the moment, so for the bending moment. I'm not going to explain what is the shear force or the bending moment. There are other ways to look at it. I'm not going to waste time in the theoretical part, and maybe I'm going to do a video regarding those, okay? So far is to know shear force and bending moment at that point. Okay, so the way to solve this is that you break the beam, okay? And this breaking up of the beam will look like this, like this. And you will have this distributed load, okay? So it's all this breaking down. So you will have this and that. You get it, right? So this one is your point A, and this one is your point. In this case, it could be point B, but you don't need to break it right at point B, although the problem tells us that. In this case, just like a point O, okay? And in that point, you will need to put a shear force here, and then a bending moment. And this bending moment, I'm going to put M here. And you need to calculate if these things, this shear force and this bending moment, are actually happening or not, okay? So that's the basic idea when you solve this problem. But first, we need to do something before using this method. The first part is to do the free body diagram for the whole beam. And let's just do it. So the free body diagram will look like this. So I have this beam over here. This is the attachment to the wall. And in this attachment to the wall, there's going to be a vertical reaction. There's going to be a horizontal reaction. There's nothing here except a resultant force. This is the resultant force due to this triangular distribution. So this one is really easy to get. You just get the area of the triangle. That's kind of the idea. So 60 times 15, okay, because the whole length looks 15. It's like the, base times height, okay? That's what I'm doing, divided by 2. So in this case, this reaction will give me a value of, I have everything here. So this one is, it's 450 pounds, okay? So this one over here is 450 pounds, got it. And there's also one other reaction or another thing happening at the wall. And this one, it's a moment. So I'm gonna call it moment A, okay? Because otherwise this thing will maybe turn to one ways or try to spin to the other way. So when you see attachment or cantilever, which is a technical word for how this thing is attached, you need to put 3 guys over here: the vertical part, the horizontal part, and also a moment that prevents this the beam going up or down. Okay, so having said that, let's just do our analysis for this free body diagram. This is X, and for the X part, I have RAX equals to 0, so no problem there. RAY going up equals to 450 going down. Okay, also no problem, pounds, okay. And then MA. So MA, what I'm gonna do is I'm gonna apply moment at point A, okay? So this one should be equal to 0 because I don't want this beam going up or down or trying to spin. So this guy doesn't participate, but I already have them. And I need to know how much displacement I need from point A till when I found this 450 pound force. Okay, so the displacement from here comes again from the triangular part, and triangular part, this is again something that you need to know before doing this. It's going to be located around here, okay, or kind of. Okay, so in this case, when you do that, because most of the distributed load is here, not here, okay? So in that case, that's why they are telling you, so it's 1/3 of the whole beam. So this is 1/3 1/3 of the whole beam. And if you want to know how much would be displaced, it's 2/3 of the whole beam, okay? So in this case, the whole beam is 15. Therefore, this thing is 15 divided by 3. That's the distance where I will find this resultant force due to the triangular distribution load. Therefore, what I will have here is that, okay, so minus MA, minus, because this thing I will take it as positive, and I draw this fella, I draw it going backwards, so it's a minus MA, okay? And then minus, because this thing will try to move it like this, okay? So it's again clockwise direction, and therefore this is minus 450 multiplied by 3, but sorry, by 5, okay, because this guy is equals to 5, and therefore you will have your value here that MA, I'm sorry, this should be equal to 0, of course, and MA equals to minus 2,250 pounds-feet, okay? So now I know how much needs to be the moment being applied at the wall, okay? What this minus means is that, well, you know what, I didn't draw it correctly. Correctly, it would be like this. So here is the beam, there is no RAX, there is one 450 going up, and to put this correctly, there is my MA correctly drawn, okay? And this one to, no, sorry, 450, okay? This one now is drawn correctly because otherwise this thing, this force, will produce a moment and try to move around this beam like that. And this moment is resisting this intention of spinning. That's what they are telling me. So, okay, fine. This minus just means that I draw it incorrectly here. Now I know that this one is the correct one, but the magnitude, I already have it. Okay, so now that I have done that, I'm gonna apply this method. Okay, so this method just consists of breaking up into pieces this beam, and since you already have it here, I already have it here, I'm gonna continue down here, and the answer will be drawn in this at this axis here. So here is the shear force that I need to draw, and there is a bending moment. So what I'm going to draw here is called the distribution of the shear force and the bending moment along the beam. That's what I'm going to do. Okay, so I'm going to again write it. I'm going to use another color. Let's just put it. This is again my triangle. Again, this is the breaking up of the beam, you know, and this is my point A. This I'm gonna call it point A. Sorry, this length is gonna be X because it's something that you don't know, okay? You don't know where you're breaking, or you don't care where you're breaking it. This guy is still 60 pounds per feet, that's correct. This point, I'm gonna call it point O, but in the problem, they are asking me, please, find whatever you need here at point B, but I'm just gonna put it here, okay? So this is point O, whichever point inside the beam. And what else? So this is the shear force, and this is the moment that it's internal bending moments, okay? So that is, and I'm gonna call it MO, okay? Well, okay, fine. So after this, it gets a little tricky when you have triangular distributions. So let me just put it like this. I'm gonna put it this triangle over here. It's not as easy as just finding the resulting force. It's not as easy as that. In this case, I need to find equations, okay? So this thing can be solved using differential calculus or integral calculus, but in this case, I'm going to use statics in order to solve it, or equilibrium forces, okay? So I'm going to put it like this. This is, again, this little triangle, okay? It's over here, its base, it's X, and its height, it's unknown. This same triangle should have the same slope as the original triangle. And maybe you remember that the original triangle has 15 as the base and 60 as the height, okay? So what I'm gonna do is to convert it into this one. I always put the base as 1, okay? So this guy is gonna be a 1, and therefore this guy needs to be 60 divided by 15, which is 4, okay? Now what I'm gonna do, I know that I'm doing a lot of steps here. You don't need to do all those steps. Now I'm going to multiply this guy by x. So this one is x. And in this case, this one is going to be 4x. Therefore, now I have the same triangle here. This one is my base x. Got it. And this little height here, this little height is not 60. It's actually 4 times x. That's the height of this little triangle there. How do you know that? Well, because the slope needs to be the same, okay? And the relationship needs to be the same one. So you have 15 here, and I have 60 here. The relationship should be the same one. Otherwise, the slope of this line, the hypotenuse, will change. Okay, so I have this x down here for x, and then I have a rectangle below the triangle, right? So in this case, I know the base. It's again, this one is x. And the height, hopefully you can remember this one, it's 60 minus 4x. That's the height because the whole thing here was 60. So if this piece of the height of the triangle was 4x, this case needs to be the rest of that or the subtraction. So now I have 3 figures. I have this triangle, and below that I have this rectangle. This one is x over here, and the height is 60 minus 4x. This is important in order to know how much force or bending moment I will have, okay? So that's important to remember. Now, let's just go to solve this problem. Let's just go with x. So for the x part, there's nobody going left or right. So maybe we already established that RAX was equals to 0. So you can put here in this case, well, 0 equals to 0. There's nobody going left or right, okay? Everything is happening vertically. Okay, now let's just go vertically. And if you go vertical, there's no axial load here. So let's just go vertical. What happens if you go vertical? Well, let's just see about this one. This one is minus V, that's the shear force. You can ask, hey, why are you putting it going down? And that's one way tradition. Okay, one way to answer that question is just tradition. Okay, so this one is going down, minus V. Let's see if there's somebody going up. And nobody's going up. All of these guys are going down. Oh, okay, so fine. So not all of those guys. There is a guy here that amounts to, okay, let me just see if I can go ahead, 450. So there's a guy going up there that is 450. Oh, okay, you got it. So for plus 450, and there are a bunch of guys going down, and this bunch of guys is due to this triangle, and due to this rectangle. Let's just go with the rectangle, which is easier. So hopefully you can remember how to get the resultant out of this distributed load, rectangular distributed load. So it's going to be plus 60 minus 4x, which is the height, multiplied by the base, and that's the area. So multiply by the base. So that's what I have here. And that is not big of a deal. Sorry, this is wrong. Oh my God. So this one is going down. Minus V, it's going down, plus 450 is going up, and this guy is going up. And also I'm still missing the triangle, and the triangle is also going down, so minus. Now get the area. Fine, the area is not very complicated. Minus 4 times x squared, okay, divided by 2, because it's a triangle. It's like base times height divided by 2. And this guy should be equal to 0. Therefore, from here I have that B. It's an expression, okay? It's gonna be equal to 2x squared, okay? What this guy is gonna be plus 60 minus 4x times x, because I just passed it the other way. I'm sorry, no, I'm gonna do this like this. I'm gonna move this guy to this place, but the other guys are gonna remain with their own signs. So this guy is still minus, and this guy is plus 450. Long story short, once you do algebra, you can do algebra. If you don't want to do algebra, it's fine. So this thing will give you 450 minus 60x plus 2x squared. So this one is a parabola that opens like this, okay? It's concave up. And now what we need to do is to calculate it at 3, because point B is located at 3 feet. Therefore, we need to know how much is the shear force happening at that particular length. Okay, so in this case, V, when this x equals to 3, it's just doing calculations in a simple calculator. So this one is going to be this amount of things. Okay, so that's when you need the shear force in just one point. Okay, but if you want to do the distribution or the behavior of the shear force all along this length, you need to use this equation. It's only getting this equation. So in order to get this equation, you will find the first point equals to 0. And if that happens, V equals to 450. Okay. And if you do at the end of the beam, you're going to put 15, and this thing will give you V equals to 0. You need to believe me that. Okay. So this is just as simple as this. It begins at 450, and then it's a parabola, concave up. Okay, so at the end, oops, it will get 0. That's what will happen with this behavior. Okay, so this is the shear force. Now let's just go with the bending moment. So the bending moment is a little bit more complicated when it comes to the algebra, but it's kind of the same thing that we have done here. So I'm gonna take this point O, okay, and I'm gonna say, well, you know what, I'm gonna do the sum of moments of regarding point O. And if you do that, let's just see what produces moment regarding this point O. So the shear force doesn't participate. It's passing through O. That doesn't participate. I have MA, right? I don't know if you remember this one. I should have put it. Okay, so I should put it. I'm going to put it, and I'm going to draw it correctly. So I'm going to put this MA here. Okay, so that MA, yeah, this one is correct. So that MA, I'm gonna put it, and it's, let me just put MA, and then I will put the number. So MA. Now let's just go with this one. This one is a force and will produce a moment regarding point O, which amounts to 450 times X. Okay, so this is the length, this is the force, this is the lever that will get me to this point O in order to produce a moment, 450 times X, okay? And the sign is minus because I'm thinking that this is the positive sign, okay? So that's for the easy part. Now let's just go to a more complicated part. More complicated part is the triangular distribution and the rectangular distribution. Let's go with the rectangle. So the rectangle, here is my point O. I don't know if you remember. Here's point A, fine. Everything is fine so far. So what I need to do in order to find it, it's okay, I need to locate where this resultant is going to happen. And this is going to happen at X divided by 2. So that's where it's happening. Hey, what about the force? The force, I already got it. I don't know, maybe you remember. This is the force or the resulting force belonging to this rectangular distributed load. Okay, so I just need to write that again, minus 4x times x. So far, it's just the force, and then I'm going to multiply it by the distance where that force is located regarding point O. So this over here, this distance over here is x divided by 2. Okay, that's kind of the idea. Okay, and this one will produce a bending moment in this with this sign. I'm going to do the same thing with the triangle. I already have here for the triangle. Okay, so I don't know if you remember, but this one was the resulting force due to the triangle. So I'm going to put it again, 2x squared. Okay, and then I'm going to multiply it by where this force is happening, and this is happening 1/3 x this place, or maybe 2/3 of x. And since I'm reading moments or I'm measuring moments regarding this point O, I need to move myself 2/3 of x in order to find this resulting force due to the triangular distributed load. I know a lot of words here. Okay, so this is already the force times the distance 2x divided by 3. And then again, it will produce a bending moment counterclockwise, which is not this one, okay? And this one, sorry, which is this one, but it's not the one that I'm looking for here. I'm sorry, this is wrong. This is wrong. I'm not finished yet. It's still not equals to 0. I need to put this fella. So I'm going to put it plus MO. This is a moment maybe happening at point O. I really don't know if that thing is 0 or not. I'm going to calculate it. So now I can do it equals to 0. Oh, okay. So it's a bunch of algebra here, okay? But okay, let's just try to simplify this as much as we can. MA minus 450x, okay? Let's just see what I can do here. Maybe I can do this. Minus 60 minus 4x. I know that I can, take away the parentheses and do my thing, but I'm just going to keep it like this. In this case, minus 4x cubed divided by 3 plus MO equals to 0. Okay, so it's still not very pretty, but it doesn't really matter. Now, this guy, I already know it. Okay, so this is 250 minus 450x, okay, minus, I'm going to just do the same thing, minus 4x, x squared divided by 2, minus 4x cubed divided by 3 equals to minus MO. So what I just did, I just passed this guy over here, and I'm gonna evaluate this minus MO regarding x equals to 0. So if I put this one equals to 0, MO equals to minus 250. Hopefully you can see that. Everything is 0 here, but this guy is not 0. And since I have a minus here, I just put it all the way there. Therefore, my bending moment will look like, I'm going to do it with, again, minus 250, okay, so that's where this guy starts. And then I'm going to put x equals 215. And if you do that, MO, you need to believe me that this guy will give you 0, okay? And if you do that, so take a look, this is a cubic equation. It looks a little bit weird, but you can do it. And in this case, you will get from the bottom to 0, okay? Hey, what about the value at 3? At B, which is 3 feet from A. Okay, well, so as we calculate this one, okay, so we already have the value for this one. Now I want to calculate the value for M B. So this is the same thing as MO when x equals to 3. It's the same thing. And this guy is going to give me minus 1,152 pounds feet. You need to believe me that. Whoops. That is actually happening. And finally, I want to show you that I grab these equations. So you have the shear force and it's beginning at 450, okay? And then it dies at 0 when the length of the beam is 15. And then for the bending moment, it starts at minus 2,250, which is this point over here, and it ends at 0 when you are doing 15. So this one is a quadratic equation. This one is a cubic equation, but you can calculate it with no much of a problem. And that's the end of this problem. So I will see you later, guys.